Alright guys, in today's lesson we're going to be studying electric circuits, and there are a few different kinds. We have series circuits and parallel circuits, and some of the things that we're going to have to calculate about those two are equivalent resistance, and also we're going to need to learn how to use meters and apply conservation of charge correctly. And then lastly, there's some equations about electrical power and energy that are going to help out. The bookwork that we're going to do, so this is going to be the second page in your notes, is going to be questions 49 to 99 on pages 129 to 133, and you'll follow that with the aim, what are the properties of electric circuits. After you have that done, I need you to copy down this do now right here. We don't need to do it, but we'll do that in class. So the simplest versions of electric circuits that we have could be described using this diagram, where you just have a battery, a resistor, a closed loop, and electrons flow on it. It's pretty much that simple. Let's use Ohm's law to calculate the current in this circuit. So we know that the equation is going to be I equals V over R, and the voltage in this battery is 12 volts, and the resistance is 2 ohms, so the current must be 6 amps. So down here at the bottom I have 3 different versions of circuits, and these are animated. I can show you in class, but even as still images they have some value. So we're going to label these with their different types. This one is going to be considered a parallel circuit, and the reason is because the little electrons that are flowing, they are able to flow along multiple pathways, and those 2 pathways are parallel to each other. So that's like this one, that's one of the parallel pathways, and then we have this one, which is the other parallel pathway. This one would be considered a series circuit, meaning that it goes like this, but it goes down one resistor and then down the other resistor, and they're in series, meaning all the electrons have to flow through the same path. And then the last one would be considered a simple circuit, because it just has one resistor, and of course there's only one path there. Alright, so let's talk about series circuits first. In a series circuit, you would see a diagram pretty much like this. There's going to be one loop, meaning there's one pathway for the electrons to flow on, and it'll have to go through 3 different resistors in this diagram, meaning that each electron will have to pass through each resistor. So it's going to be resisted 3 times before it returns to the battery for another push. We can talk about this concept called equivalent resistance. Down here, it has an equation like this. It says Req is R1 plus R2 plus R3, and that just means that if you took all of these resistors out and you replaced them with one resistor, the one resistor that would be equal to all 3 would be just the sum of the 3 resistors, and that makes sense because the electron has to pass through each one of them anyway, so if you just add up their resistances, that would be the equivalent resistance. Now that's only true for a series circuit, and you can find this equation on your reference table under electricity for series circuits. But in addition to that, you also have these current equations and this voltage equation. And the current equation is telling you that the current through this resistor, that's I1 or R1. I1's current is going to be equal to I2's current, which is right here. There's I2's current. And I3's current is going to be equal to resistor 3's current, just meaning that the current, or the electrons flowing, are going to have to be the same electrons here as here. So you're going to get the same current through each resistor. Now check out voltage. We have the voltage gain here at the battery. So this is where all the voltage is gained, all of the push for the electrons is gained. But voltage is lost every time you go through a resistor. We call these voltage drops. So you have a voltage drop at resistor 1, a voltage drop at resistor 2, and another voltage drop at resistor 3. And one of the things we know is that all of the voltage will be lost by the time you get to the battery, and different amounts of voltage will be lost at each resistor depending on the resistances, but you get this like stepwise voltage drop. So you lose some voltage here, you lose some voltage here, and you lose the rest of the voltage here, so that by the time you get back to the battery, all the voltage has been lost. Now in parallel circuits, some things are different. Some things are the same, but some things are different. So in terms of things that are the same, we still have our battery, it's still the source of voltage, and we still have voltage drops at each resistor, but the way this plays out will be different. So let's first talk about current. So the current which goes through the battery is going to be I. So here's I, and that's the current at the battery. And the current through each resistor is not going to be equal at this time. In this case, because electrons could choose to flow this way, or this way, or this way, then you're going to get different currents flowing through each resistor. And that's why we say that the currents simply add up to equal the battery. They're not equal to each other. So this current is going to add up to this current, which will add to this current, and all of those currents will come and be recognized at the battery. So 3 currents converging into 1, just like that. Additionally, in this guy, we have voltage drops, which are all equal to each other at all points. So the voltage gain at the battery is V, and V1 is the voltage drop at resistor 1. And it's saying that it's equal to the voltage gain at the battery, which just means that if you gain 12 volts of potential difference at the battery, you'll lose 12 volts at resistor 1, you'll lose 12 volts at resistor 2, and you'll lose 12 volts at resistor 3. Or in other words, if you're an electron passing through this circuit, you will lose all of your voltage at each one of the resistors, so that when you come back to the battery, you have no voltage left. Now lastly, we need to talk about the equivalent resistance equation, and it says that the inverse of equivalent resistance will be equal to the sum of the inverses of resistance at the resistors. So quite literally, when we're doing these mathematical equations, we'll look at the resistance at R1, the resistance at R2, and the resistance at R3. We will take their reciprocal and add them together, and then we'll take the reciprocal of that sum, and that would be the equivalent resistance. So there are some tricks for some like mental math, I suppose. If you are trying to calculate the equivalent resistance, which is the combined resistance of all the resistors in a circuit, you'll have different strategies depending on the type of circuit you're looking at. So if you have a series circuit like this, you would just take their resistances and add them together and get 16. On the other hand, if you're looking at a parallel circuit like that guy, you need to acknowledge that the electrons can come through and they're going to split and come through each resistor and then converge again afterwards. So the resistances at these 2 resistors, they don't simply add up. Instead, they're going to provide 2 separate pathways for the electrons to flow. So the electrons actually encounter less resistance overall in this circuit because they have 2 separate pathways on which to flow. It would be like thinking about like doubling the width of a hallway or doubling the width of a sidewalk. You would give twice the amount of pathways, and there would be literally half the amount of resistance. So that is, of course, a description of an inverse relationship between the number of resistors and the equivalent resistance. So that just means if I take these 2 resistances, that's twice the pathways, I'll have half the resistance, so overall it's 4 ohms. If you had 3 resistors at, let's say, 9 ohms each, as you have in this diagram, then you would take the 9 ohms and divide it by 3 to get an REQ, or equivalent resistance, of 3 ohms, because you would say 3 pathways would be 1/3 the resistance. If it were 4 pathways, it would be 1/4 the resistance. But to do this trick, you do need to have 3 resistors that are all the same value. If they have different values, you would have to use the equation from the previous page that said 1 over REQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Alright, so let's try this one. For resistors in parallel, the equivalent resistance of the circuit is less than the value of any individual resistor. Let's prove this by calculating that the equivalent resistance of a parallel circuit with 1 2 ohm and 2 1000 ohm resistors. So this question, or this challenge, is telling us that if you were to find the equivalent resistance of these three resistors, that the equivalent resistance would be less than any of these. Now, I chose numbers to make it seem improbable that this could be true, because obviously this is a huge resistance, that's a huge resistance, and that one's really small. But my claim is that the equivalent resistance will be less than 2. I'm saying that the equivalent resistance is less than the value of any of the individual resistors. So let's see if that's possible, that two 1,000 ohm resistors and a 2 ohm resistor could have an equivalent resistance of less than 2. So we can't use this mental math trick because all these resistors are not all the same resistance, so we're going to have to use our standard equation from the previous page. So there it is. Let me plug in some values now. And I'm going to plug these into my calculator and get an answer. So 1 over REQ is equal to 502 over 1,000, which would mean that REQ, after we take the reciprocal, is 1,000 over 502, and of course we can simplify that to 1.992, and there's some more digits, but this is going to be ohms, of course, and I just wanted to point out that this is the equivalent resistance, and it is less than 2. So when you go through all of these resistors, opening up more pathways will always decrease the overall equivalent resistance, even if the other resistors are really resistant. Alright, so let's use some mental math to just calculate equivalent resistance for compound circuits, which are circuits that have elements of series, like this guy, which is part series, part parallel, and also elements of parallel with series in between. Alright, so what I would point out here is that these two guys can be collapsed into one resistor with a 4 ohm resistance, because the two pathways, so it's going to be half the resistance each. And then it's going to be this guy plus a 4, so 8 plus 4 is 12. So that's how you would do that one. For this one, I would point out that these two can be combined into a 4 ohm, so that's what you see here. And then the 16 and the 4 can be combined into a 20. The 10 and the 10 can be combined into a 20. So now we have two 20s in parallel, and they can both, because they're representing two pathways, they can be combined into one 10 ohm resistor. Let's do a sample problem. We have three resistors with resistances 4, 6, and 8 ohms respectively connected in series to an applied potential difference of 36 volts. I always like to draw a diagram to help me understand. And in part A, I'm asked to calculate the equivalent resistance. For a series circuit, you just add the resistances up to equal the total. So there's the equation. I'll plug in values. And 4 plus 6 plus 8 is 18 ohms. So the single resistor that could replace all three would be one 18 ohm resistor. In part B, we're asked to calculate the current through each resistor. So in this case, because each electron must pass through each resistor, all of the currents will be equal. If I calculate the current through each resistor, I can just calculate the current for I, and I'll use REQ as my equivalent resistance, and that's how I'll know the current at every resistor. So I is going to be equal to V over REQ. And the voltage drop at the battery, or the voltage gain at the battery, is 36 volts, and the equivalent resistance we just solved for is 18 ohms, so that means that the current is 2 amps at every one of the resistors. Now in part C, we want to know the potential drop across each resistor. So to do that, I just put in Ohm's law, and I said that V1 is IR1 for resistor 1, V2 is IR2 for resistor 2, and V3 is IR3 for resistor 3. I'll plug in values. So in each one of the cases, the I was 2 amps, because in this equation we can see that they all have the same current, but they do get different values for resistance. So after calculation I get 8 volts at resistor 1, 12 volts at resistor 2, and 16 volts at resistor 3. So that's my final answer for everything, but there is a check you can do, which is that the voltage gained at the battery should be equal to the sum of the voltages lost at the resistors. So 36 volts was the voltage gained at the battery, and the voltage lost at each of the resistors was 8, 12, and 16. If you add all of those up, you do get 36, so our check goes through, and I think we can be sure that our answer is right. Alright, let's do a sample problem for a parallel circuit. 3 resistors of 4, 6, and 12 ohms are connected in parallel to a potential difference of 12 volts. So there's my diagram that helps me understand what's going on. So guys, in part A, it asks me to calculate the equivalent resistance. For a parallel circuit, the equivalent resistance is going to be calculated like this. And I can pretty much do this relatively straightforwardly, so let me plug in values. So my answer for 1 over Req is 6 over 12, which means that my answer for Req is 12 over 6, or of course 2 ohms. In part B, we're asked to determine the potential difference across each resistor. So you may remember that in a parallel circuit that the voltages are all equal to each other because you're going to lose all of your potential difference after each resistor and before you return to the battery. So as these electrons come through, they're going to split up, they'll take different paths, but they'll lose all of their voltage right here, and then they'll come back and they'll regain their voltage at the battery. So that makes questions like this one extremely easy to solve, because if the voltage at the battery was 12 volts, then that's going to also be the amount of voltage lost at each resistor, so my answer for B is 12 volts. The voltage at the battery is 12, and the voltage lost at each resistor would be 12. For part C, we're asked about the current through each resistor, and for a parallel circuit, the currents will be different at each one of the resistors, but they'll add up to be the current at the battery. So the electrons go through here, they all go different paths, they split up, but then they add back up to come back to the battery. So I is I1 plus I2 plus I3. And Ohm's law tells us that current is voltage over resistance, or I is V over R. So I'm going to put in a V over R for each one of the I's, because I equals V over R. So I've done just that. I said that the voltages would all be the same, but that they do have different resistances. So after plugging in, I get 12 over 4, which of course is 3, 12 over 6, which is 2, and 12 over 12, which is 1. So that's the current at each one of the resistors, 3 for R1, 2 for R2, and 1 for R3. And overall, although they don't ask us for this, the overall current is going to be 6 amps. But really my answers are 3, 2, and 1. Amps, amps, and amps. Alright, let's talk about meters and conservation of charge in electric circuits. An ammeter measures current and a voltmeter measures potential difference. So in these diagrams, you can see the correct way to place the ammeters and the voltmeters. The voltmeters always need to have a separate pathway drawn parallel to a resistor to measure the voltage drop at that resistor. And an ammeter actually needs to be drawn in series with the resistors whose current they're measuring. So this ammeter is drawn in series with R1 and R2, and this voltmeter is drawn in parallel with R1. The voltmeter only measures the voltage drop at R1. Now, in a parallel circuit, we have an ammeter which is still drawn in series with R1, and the voltmeter is still drawn in parallel with R1. So there's a little bit of a difference here, though, because the voltage drop at both of these resistors would be the same. So this voltmeter can measure for both. So in short, voltmeters are drawn in parallel while ammeters are drawn in series. As a mnemonic device, one thing that I can advise people to think of is this, as VP. It's sort of appropriate this time of year because this is sort of like ramping up for election season, whether it's a presidential election or an SGO election. And oftentimes, people who are running for vice president begin their speech with, as vice president, so as VP, ammeters in series, voltmeters in parallel. All right, and then also on this slide, we need to consider that electric charge has to be conserved. So in this diagram, we can show that because we can look at what happens at junction P. So consider that at junction P, we have some currents which are coming in, namely a 7 amp current going in, and we have some currents going out, mainly a 3 amp current going out and a 4 amp current going out. And this does show conservation of charge because if 7 amps come in and 3 and 4 amps go out, then you have the same number of amps coming into point P as you have going out. This would have to be true at any point in the circuit. The number of amps that enter that point would have to be equal to the number of amps that leave. And I have a couple more equations here for electrical power and energy. Take a look at this equation. Power is work over time. We've done that one before. Remember that power is measured in watts. And electrical power is the product of potential difference and current. So you're going to see this equation a lot, P equals VI. But in addition to power being the product of potential difference and current, we can also say that power is the current squared multiplied by the resistance, or even the voltage squared divided by the resistance. So all of these equations are usable, they all work. You can use any combination of them, and they're all in your reference table. Check the electricity section and you'll see it look just like this. Let's try at least one of them in action. A potential difference of 60 volts is applied across a 15 ohm resistor. Calculate the power dissipated in the resistor. So I labeled the things I know. It seems that we have a voltage, a resistance, and a power. So my instinct is telling me that we have power, voltage, resistance. We may as well use P equals V squared over R. And I get 240 watts of electrical power. Electrical energy and electrical work would be the same thing. We're going to use the symbol W to represent it, but its unit is going to be joules. And the equations that you can use are down here. Also, this is going to be on the electricity section of your reference table. But W is PT, but it would also be equal to VIT, which would also be equal to I squared RT, which is equal to V squared T over R. Let's try this one out in a practice question. A current of 0.40 amps is measured in a 150 ohm resistor. Calculate the total energy expended by the resistor in 30 seconds. Let me label the things I know. So I'm aware that I have an I, which is current, I have an R for resistance. They're asking me for energy, which is W, and I also have a T, which is time. So when I'm looking at the equation for the things I know, it seems like we're going to be looking for work, but we have a current, a resistance, and a time. So let's use W equals I squared RT. So I'm going to be doing 0.40 squared times 150 times 30. And when I go through that calculation, I get 720 joules of electrical energy or work. So I have 3 pages of pair up and summary for this guy. What you'll see here is a sort of generalized pair up. But here we have some extra questions that are just for series circuits, and down here only for parallel circuits. So we'll find that those are all alike in some way. And here is the summary question page. So copy down these questions. The multiple choice ones, don't copy them down, I'll make copies. But please do copy down these. And thanks for watching. I'll see you in class.